In this video, we're going to be talking about modeling interacting systems. This is one of my favorite topics that we cover in the entirety of class. That's probably because this is one of the topics that doesn't get covered in pretty much any other physics class, but it uses the same type of quantitative reasoning that we're used to thinking of to explain complex systems in the real world. So in this video, I'm going to be in detail going through the Lotka-Volterra model, which is a simple model for ecology. So it looks at the interactions between predator and prey populations. So imagine I have this beautiful pastoral plain. Here's my little bunny, and she's hopping along, chowing down on some grass. And in comes another bunny, and well, sparks fly, and before you know it, there are a bunch more baby bunnies. So just having the single population, we can think a little bit about turning the growth of this population into numerics. So in this population, the rate of change of a population is proportionate to its size. So um, more bunnies make even more bunnies. So this generation started with 2 bunnies, and you got 5 bunnies out. So that those 5 bunnies, each pair of them is going to produce 3 bunnies. And so the population grows exponentially. So we have the rule that animals reproduce proportionately to the amount of food they have to eat. So if you don't have a lot of food, you can't use that energy to create babies. In our model ecosystem here, we've got so much grass that the rabbits always have enough food. But this is about interacting systems. So in our ideal ecosystem here, we also have some foxes. So the foxes eat the rabbits, and as the foxes eat the rabbits, foxes then produce more foxes. In this model, foxes only eat rabbits, so the entire food supply of foxes is dependent on the size of the rabbit population. So this is a really simplified ecosystem. And we're going to assume that there's no evolution and no environmental change. So what happens now is going to be the same as what would happen in the future. So if I want to now take these things and start modeling them, imagine, so R is going to be my rabbit population. In the absence of anything else, if I have only rabbits growing based on their food source, they're going to have some birth rate, so the birth of the rabbits, and that's going to be exponential growth there, minus the death rate of the rabbits. These together are going to equal the rate of change of the population of rabbits. The rate of change is always going to be proportional to the population itself. What happens with the foxes now? There's some natural rate at which they get old and die, but the growth rate of foxes depends on how much they have to eat. So it's going to be the population of rabbits. So that's our R here. And then it's going to have some scalar outside of it. So this is the birth rate of foxes. So foxes here are happily eating rabbits and reproducing. So we need to subtract that from the rabbit population themselves. So there's some rate at which rabbits are being eaten times the fox population times the rabbit population. So the rate of change of rabbits is now going to be decreasing dependent on how many foxes there are and how many of those foxes can eat the existing rabbits. So this is the basic dynamics of our system. We've got this spelled out a little bit more explicitly as differential equation. So I've got the rate of change of the rabbit population is some constant times the rabbit population. So this is the combined birth-death rate. And then it's going to decrease depending on the number of foxes times the population of rabbits. There's also a rate of change of fox population. So this depends on their birth rate times the number of rabbits they can eat times the fox population. So this is going to be how many foxes get produced based on the current size of their population and the current size of the rabbit population. And then the foxers are going to die off at some rate as well. So this is now my coupled nonlinear set of differential equations that models this interacting system. This is something that we can study the solutions of. So here are some of the solutions that I've plotted in Mathematica. So the prey population is on the bottom, the predator population is on the y-axis, and then we have different values for the coefficients A, B, C, D. So we can imagine all sorts of cases of different behaviors. So we can start out with behavior where we have, say, so A is equal to 1, so this is the exponential growth rate of rabbits. So the rabbit population is growing exponentially, but no foxes are eating them, so their population is not decreasing because of the foxes, but that also means the foxes are not reproducing because of them, and the foxes are dying off. So what does this show? This shows that you have an exponential increase in the rabbit population while you have an exponential decrease in the fox population. So this is the non-interacting model of the system. What if, on the other hand, the rabbits here do not breed or die? They get eaten off constantly by foxes. The foxes reproduce but don't die. So in this case, you have a linear decrease in the prey population while you have a linear increase in the predator population. So since rabbits aren't born, there's no exponential growth, and since foxes don't die, there's no exponential growth, but the rate at which they can grow is capped by the population of the rabbits, and that is decreasing linearly. We could have another case where this one makes no sense ecologically, but if you're just playing with parameters, you can see what this is. So ecologically, this would be rabbits are born and grow at some rate. Rabbits are not being eaten by anything. Foxes are born and grow at some rate. So this is the unphysical part, because as foxes are born, our model requires that they eat rabbits, but here I don't have anything saying that the rabbit population is decreasing from predation. So this is unphysical, but let's just go with the parameter space. And foxes don't die. So this is exponential growth for both of the populations. This last case is a lot more interesting. This is where a lot of the interesting dynamics begin to show up. In this case, we have, I guess, constant rates for everything. So rabbits are born, they get eaten, foxes eat rabbits and are born, and they die off at some rate. I've set these all to 1, but depending on the biology of your system, you might need to vary this. So what's going on here, we have, so I've got these red dots of where I've started my solution.
So I start here with, here's my population that has, I guess, 2x prey and 2 predators. Maybe this is like 2 million of each or something like that. So what's going to happen here? So here there are plenty of rabbits for the foxes to eat. So the foxes start eating a lot of rabbits and they start increasing their population. Then we come to a point where there's so many foxes that the rabbit population can't sustain them and the fox population crashes. And then when there are no foxes to eat the rabbit population zooms up and rebounds. And once there are plentiful rabbits around, the foxes start eating them and growing their population. And so you end up with these closed cycles where you have plentiful prey and then a predator boom in population, which decimates the prey, and then the predators have nothing to eat, their population drops. There are no predators, so the prey population soars, and then the cycle repeats. So there's going to be some phase lag to all of this, and that sets up a periodic cycle. So this cycle can now go on indefinitely. There are a few other models that are very common here. You can use this very similar model to the Lotka-Volterra model to look at cyclic chemical reactions. So ones where you have 2 reactions where one reaction catalyzes the other reaction. And again, you end up with these closed cycles in population space. Another example that is one that you've likely heard of in the news is the SIR model. And so this is a model for epidemiology. This is modeling 3 populations of people. There are people who are susceptible, there are people who are infectious, and there are people who are recovered. There are rates of transmission within these populations. So infected people can only infect susceptible people, for instance. This is something where epidemiologists have been able to model different types of outbreaks. And this is really quite accurate for things like the flu and so on. You can track micropopulations based on data from things like Google Flu and figure out what the coefficients between the interacting terms are in the model. So how infectious was that strain? What is, latency in times when people are infected and the peak infectiousness of your population? That's these peaks that politicians were talking about in the news. So how do you predict that? When are the cases going to be dropping? That's something that you want to know in advance. And that's really hard to predict for new pathogens because this depends so much on both human behavior and the biology of the new disease. So that's why millions and millions of dollars have been going into studying these models, plus more and more complicated variations of them involving things like stochasticity, networks, so on. I will put some links in the description to other YouTube videos on these topics that you might find interesting.